Potential energy is our next topic, and the conservative forces that we discussed in the last video, the main impetus behind defining them is that they allow us to define a potential energy. So just to remind you, conservative forces are characterized by two properties. One is that they depend only on position, and the other one is that the work is independent of path that a particle takes between 2 points. And this is a slightly different expression. This is a line integral but along a loop. So if you have point A here and point B there, the second condition on a conservative force is that if we take two different paths from A to B, the work should be the same in each case. So this is WAB, and this should also be WAB. However, if we reverse the direction along this path, then the work done is minus WAB, and the total work around this loop is 0. So if the total work around any loop is 0, that's equivalent to the condition that the work is path independent. So this is a more compact way of writing the same thing. Okay, so if we have a conservative force, defining potential energy is relatively easy. It's sort of a two-step process. First, we pick an arbitrary point where the potential is chosen to be 0. And this can be anywhere. And in fact, you don't have to have the potential equal to 0. It could be a constant, but the conventional choice is to choose the potential to be 0 at this point. This gives us then the ability to define the potential energy at any other point as minus the work required to go from point R0 to point R. That is the minus the integral, the line integral, from R0 to R of that scalar dr. In other words, the potential energy is minus the work done by a force as a particle travels from R0 to R. So this is actually a definition. That's what that triangle means there. All right. So we can see now that these conditions are actually necessary for this to be a well-posed definition. F depends only on R, not on any other condition, so that means that potential also only depends on R, on the position, on nothing else. It will not change over time, for instance. And this integral is also well defined. You don't have to specify a path, only a position. And that's what makes this work. So let's now do an example. You're going to look at the potential energy of a mass little m near a planet of mass big M. Essentially what we have here is a planet with mass big M. And then we'll have a second planet which is smaller. That is some distance r away from the big planet. We then have to pick a point R0 where the potential is 0. Conventionally, we pick in this case R0 at infinity. So if we choose a path all the way to infinity that the planet might take, then over at infinity the potential energy is set to be 0. And I'm also going to then choose to call any point on this path R prime. Then in order to define potential energy, we have to calculate the work and show that it is path independent. So we know that the force of gravity between two particles is equal to minus g little n capital M over r squared r hat. So it's the force of gravity there. That's a little small. Hopefully you can see it. So that's the force of gravity. We need now to calculate the work done by that force as the planet moves in from R0, which is at infinity, to the position R. So that's the integral. R prime here is any point along the path, and R is the final point of the final position of the planet, where we're interested in finding out the work, or the potential energy. And we're going to do this in spherical coordinates. And if you don't remember how to work with spherical coordinates, there's a math interlude on the issue, which I recommend that you peruse. But and if you do that, you will know that the differential displacement in spherical coordinates, the vector dr prime, has the following form. Where this is the r coordinate, the theta coordinate, and the phi coordinate. Now, r hat prime is just this in spherical coordinates. So this gives us, conveniently, this. So our integral here, the work integral, I'm going to put it over here again, just is therefore equal to just minus gmm, and then the integral from infinity to r, not a vector anymore, and this is just a single integral of the r prime over r prime squared. So it's automatically parameterized because it turns out that this, in the spherical coordinates, this line integral only depends on one variable, so we don't have to carry out any explicit parameterization to make this work. Okay, and then we just have to calculate the integral. Okay, now that's it. So the potential energy is minus this work. So this gives us which is independent of the path. So it's a well-defined potential energy. So that's an example of potential energy for a specific concrete force, and there are many others, of course. Now let's, for a moment, step away from the specific to the more general, And let's say that we have point R1 here and a position R2 over there. And we are interested in the movement of a particle from R1 to R2. And you want to figure out what the work is done, what work is done on this particle when it's going from this point, from point 1 to point 2. Okay. We also have point R0 over here because the force is conservative. So at this point here, we've chosen R0 to be the point where the potential energy is 0. Now, if I want to calculate the work of going from R1 to R2, because this force is conservative, it doesn't matter which path I take. So I could take that to be equal to the work of going from R1 to R0 plus the work of going from R0 to R2. And just to save some space, I'm just going to call this W12 equals W10 plus W02. Okay. Now, if I move the particle in the opposite direction, then the work changes sign. So this becomes equal to minus W01 plus W02. Right. Now, the work to go from point R0 to point 1, that's equal to, minus that work is equal to the potential at point R1. Right? This is U at R1. So therefore, W12 is U at R1 minus U at R2. And I'm going to call that minus delta U between 2 and 1. Now let's see what effect this has on the work energy theorem. So we have the work energy theorem, which says that the change in kinetic energy is going from 1 to 2 is the work related to going from 1 to 2. Let me just change this here. It should be 1, 2. So that is equal to minus the change in the potential. In other words, if we have been dealing with a conservative force, we can rewrite this, if we like, that the change in the kinetic energy going from 1 to 2 plus the potential energy going from 1 to 2 is 0. In other words, the total energy is a constant of motion. So we're now starting to approach the statement that energy is conserved, which we know is true, and this is the first step in that direction. One way to look at this, the work energy theorem in this context, is to consider here the particle that we're working with. It has some kinetic energy T, and then we have reservoirs So this is the reservoir of potential energy of type 1. Here's the reservoir of potential energy type 2. And there's some level of the potential energy in each of them, so they contain a certain amount of potential energy. Then forces act on the particle. So we have work from force 1 here, and we have work from force 2 there. And what the force does, is that it drains potential energy from the reservoir and adds to the kinetic energy of the particle. Same thing for this force over here. You might have, of course, some non-conservative work, which might also come in, but there's no potential energy reservoir associated with it. This is why this minus sign in the definition of the potential energy up here is important. When it reflects the fact that if you do positive work on this particle, then you're draining the potential energy from this reservoir, so that the change in potential energy is negative. On the other hand, if you do negative work, so that the particle slows down, then you're filling up the potential energy reservoir, so that the change there is positive. So that way they always have opposite sign. So generally speaking then, if you have multiple forces, let's say that we have that the change in kinetic energy is equal to some gravitational work plus some work due to a spring, and that is minus the change in the gravitational potential energy plus the change in the spring potential energy. So we get that, so that the change in the total energy, potential plus kinetic, is 0. If we have non-conservative forces present, then we can still use the work energy theorem. We get that the change in the kinetic energy is the work done by the conservative forces, and this is minus delta U, plus the work done by the non-conservative forces. So in general then we get that the change in the total energy, that is the change in the kinetic and the potential energy, equals the work done by the non-conservative forces. And that's a more general formulation of the work energy theorem and the presence of conservative forces and therefore potential energy. So what happens, for instance, if the non-conservative force happens to be the force of friction, then we know that the work done by friction is done by a force that's always in the opposite direction of travel, so that's less than 0. So that means that the total energy, kinetic plus potential, is always diminishing in the presence of friction. As long as the particle keeps moving, once it stops, of course, no further work is being done. So that's a brief introduction to potential energy. So again, because it's important, I'm going to say it one more time. The potential energy is equal to the work going from some reference position to the point R, with a minus sign in front, very important. And we write that as an integral. Now, this is nice, but the problem with integrals is that they depend on what's happening along a path. What we really would like to do is find an equivalent definition that relies only what happens in the neighborhood of one point, kind of a differential definition of potential energy. And that's what we're going to do in the next video.